In general, functional programming is conceived from mathematics. And as a result, there are some strict rules associated with functional programming, just like there are with mathematics. And we need to follow those rules to be doing pure functional programming, which is largely what I'm going to be talking about here. And there is some odd lingo often associated with it, and I'm going to talk about that at the end of the presentation. There are two main branches of programming. One's called functional, the other's called imperative. We're probably mostly imperative programmers. We've been dealing with C and C++ and C# and Visual Basic, and all these languages are all considered imperative languages. Some of the capabilities of these or features of these two languages are that pure functional programming has no side effects, whereas in imperative programming, side effects must be carefully managed. Functional programming has no internal state. Imperative programming definitely uses internal state. In fact, it's an important part of object-oriented programming to have internal state. Functional programs are thread safe. They're reentrant. Multiple threads can call the same function with no concern about them stepping on each other in any way. We'll talk about that at some point in this course. And with imperative programming, it requires a lot of thread management, locks and mutexes and these sorts of things. They can be cumbersome and difficult to deal with, and they can have their own bad side effects. Functional programs are easier to parallelize, and for some of the same reasons of thread safety and imperative is difficult to parallelize. It's easier to reason about functional programs. They're very logical and straightforward, and they also have relatively low syntax, and I'll show you that. And imperative programs are often more difficult to reason about for a variety of reasons. Functional programs are highly testable, whereas imperative programs can be difficult to test, and I'm sure we've all experienced the difficulty of getting good, high-quality tests for our software. There's less code noise in functional programs. The syntax is very lightweight and very powerful when you learn how to use it correctly, and I'll be teaching a lot of that in this course. Imperative programs often have a lot of structural code necessary to just make them work, and this creates a fair amount of noise in the code. Functions are composable, and we're going to talk in detail about composition of functions. It's a very powerful tool, and we will use it extensively. Imperative programs are usually not composable functions or composable methods. And best of all, function starts with the word fun. So let's have fun with this. And imperative starts with the word imp, and I'll leave you to decide what you think that might mean. Pure functions, for any given input, always produce the same output. They also can only accept valid input. They have a particular domain, and we'll talk about that, and only members of that domain can even be inserted into them. Anything else will cause a compilation error. They never produce invalid output. They may produce the same output for different inputs. That's perfectly acceptable. They may have a restricted set of possible outputs, so they may only produce a few different values. That's perfectly okay as well. And they never produce side effects, and they never rely on any internal state. So what are side effects? Well, side effects are when a function, or what we would call a method, because if it's producing a side effect, it can't be a function. So in object-oriented programming, especially in C#, we refer to them as methods. And methods often produce side effects, and these can be important. An impure function goes out and talks to a database. That's a side effect. Or it prints to the screen. That's a side effect. And those are relatively mild, unless, of course, your network goes down when you try to talk to the database. Then you get an exception, and you have to deal with that. So there's a lot more that you have to manage in impure functions. And what I'm going to be showing you is how we can limit the area of impure functions, the areas where we talk to databases or punch out websites or whatever it may be. Those impure functions need to be carefully managed, and by moving a lot of our code to the pure functional side, we have less to deal with and less for those side effects to mess up when something does happen. and we will be working through those problems too. So side effects are not bad. They're useful and necessary for programs to work, and that's why we have imperative programs or object-oriented programs to do that kind of work. But they need to be controlled. Side effects have to be carefully managed so that we can ensure that if anything bad happens, such as an exception, we handle that properly. And side effect is when a function uses something outside of its scope. All that means is that the function is reaching out and touching some other part of the program that's not within its immediate scope. Or pure functions do not rely, or non-pure functions may rely on side effects from other things, outsiders coming in and touching their scope, and pure functions do not do that. Composability. When a function has an output that matches the input of another function, those two functions can be composed together. And when they're composed together, as here, function A and function B, they made up their output to input, and they form a new function with an output and an input. That's the basics of composability. We'll talk about that in more detail as we begin to work on it. And it ends up with the same input as the input to function A and the same output as the output of function B. So it becomes a whole thing wrapping that. And what this is in between, what the in-between part is, doesn't matter. Once it's wrapped in an entire function, we no longer have to worry about wiring it up. So let's talk about domain and codomain. The domain of a function is all the entire group of values that are allowed to be entered into the function. And the codomain is the entire allowable set of possible output values. The function may not put out everything in its codomain, and I'll show you that in a minute. But let's just get those two terms straight. There's a domain and there's a codomain. The domain is the input, the codomain is the output, and it's a set of values. When a domain or when a function does not return all the possible values of its codomain, we call that the image on the codomain, or sometimes it's called the range, though the term range is sometimes confused with the codomain. There are functions where they are equivalent, the image or range and the codomain, and we'll talk about that in just a moment. So a function can take in some total set of values but may only put out a partial set or a subset of its codomain. That subset, you can think of it like the sine function. The sine function can take in any real number. However, it can only put out numbers between -1 and 1, or from -1 to 1, more precisely. So functions can be categorized or by certain properties that they have. The first one here in column 1 is not a function. And the reason it's not a function is, well, first of all, the small blue boxes are the domain, and the small yellow boxes are the codomain, members of the codomain more specifically, and members of the domain for the blue boxes. For the function in column 1, you see that A produces either an A or a B. So some side effect must be coming in and making that determination which it's going to produce. And therefore it's not a function. That doesn't mean it's invalid. It's probably perfectly usable that way, but it's not a function. The second column shows what a general function looks like, and this obeys the rules of functions. A maps to A and B maps to A. That's perfectly acceptable. Nothing maps to B, which means if A, B, C, D is its entire codomain, then A, C, D is the image on that codomain. This function can only produce an A, a C, or a D. It can never produce a B. But it always maps from a single one to a single one. It can map from a single one to the same one, that's fine. When a function does not map any two values to the same value, from the domain to the codomain, but does not cover the entire codomain. It covers a subset, as in column 3, where it only covers A, B, C, and D, and there's another element, E. It doesn't use E, it never produces it, but A always produces a B, and if you get a B, you know it always came from an A. Okay, we call that injective or one-to-one. When a function, every single member of its domain maps to a member of its codomain, even if there's two members of the domain that map to a single member of the codomain, we call that surjective or onto. Finally, if it does both, if it maps one-to-one and it maps to the entire codomain, it is both surjective and injective, and we call that bijective. Bijective is very important, and I'll talk about that in just a second. So why are these characteristics important? Well, first of all, a function is invertible if and only if it is bijective. So that last column where it maps one-to-one and onto, that function is invertible. We can take and switch around the domain and the codomain and have a new function that maps from what was the codomain to the domain. And that's an invertible function, and they're very useful. And two sets, A and B, have the same cardinality if and only if a bijection exists between them. And what that means is that they map one-to-one, and therefore every single element is of the same the whole set is of the same cardinality. There's exactly the same number of elements or size to that set in both of them. They're identical in that regard. And finally, the lingo. If you go out and you read about functional programming on blogs and books and other literature, there's a small menagerie of words you'll run into, like functor and monoid and monad and endofunctor, currying and lambda. And there's others, and I only put a few up here. We're not going to talk about most of these words. We'll probably talk about lambdas. We probably have experienced lambdas in C#. C# supports them. And we're going to talk about currying. And currying's not so difficult. We will actually be building, however, these other things. We'll be building them. But I'm not going to call them that, and I'm not going to tell you which one is which, because I don't want these words, which come from mathematics, they actually, lambda comes from lambda calculus, and these others, monad and endofunctor and so forth, come from a form of mathematics called category theory, and we're not going to talk about that in this course. So it's time to roll up our sleeves and write some code, create some functions, and understand and work with how these various bits and pieces come together and provide us really solid, good code. And I will see you in the next lecture.